Hello, welcome to Analog Electronic Circuits, lecture 20. So, today we are going to talk about the self biased active load differential amplifier, differential input, single ended output. The circuit we were discussing in the last class was a setup where I had a differential amplifier, but the load was a current mirror as opposed to a regular active load PMOS on each output. Right. So, this was the circuit we were discussing, and let us assume that this current source, the tail current source, is an ideal current source. We applied at the two inputs, we applied some common mode plus V in by 2 and the same common mode minus V in by 2. Then in the last class we solved a little bit, right. We did a little KCL and figured out that if this is I and the same I has to go the other way, because the current source does not take any signal current, then that means that the voltage over here will be exactly equal to VCM, okay, which means V in by 2 drop will be created here, minus V in by 2 drop will be created across the other VGS, and I will be equal to GM times V in by 2. Okay. Here we did not take into account RDS of this particular MOSFET, we have forgotten about RDS of that MOSFET. Okay. So, that is a problem. However, that is a minor problem according to me, that we have so that is an inaccuracy in this analysis. So, one inaccuracy is that we forgot about RDS between these two terminals. We are just saying I is GM times V in by 2, that I is creating a voltage drop over here because this is a diode connected MOSFET, right. So, the voltage drop over here will be minus I by GM plus GDS, GMP plus GDSP. Okay, that is the voltage drop over here. Here I have taken into account the resistance of the PMOS, all right. Yeah, I forgot to take into account resistance of the NMOS, but here I have taken into account resistance of the PMOS. So, we have forgotten this, remember. Okay. So, if you want to take into account resistance of the NMOS, then one more. So, this I current will also drop across that extra GDS N. So, that is going to get added into this denominator. Let us not worry about it now. Okay. So, this drop in this voltage creates a response in this current in this MOSFET, which is GM times that. Okay, so, I current is pushed this way and this also is approximately I. So, I current is pushed the other way, and therefore, the current going out into the load is 2 times I, and this 2 times I, if there is no load, then this 2 times I is going to drop through the RDS of the NMOS as well as the RDS of the PMOS, and therefore, your voltage over here is going to be 2 times I times RDS of NMOS in parallel with RDS of PMOS. Okay, so, this was our analysis in the last class, and clearly there are some inaccuracies over here, right. There is an inaccuracy, I forgot RDS of this, I did not even bother with it. Okay. It is not going to make much of a difference, trust me, because RDS is anyway very large. Okay. It is a minor change in the expression is going to happen, right. And then over here also I assumed that this VCM is a constant, it is not necessarily a constant, right, VCM could be changing, in which case the impedance looking down over here is not RDS of NMOS, all right. So, all kinds of problems are there, and I had a question in the meantime that from one of the students. I had a question that why do not we just, why are we doing it so hard? We know that there are two inputs, let us call this V1 and V2, and like we solved in the class before the last class, let us just do a brute force analysis, and the circuit is not symmetric anyway. Why are we bothering? Why are we trying so hard? Let us just do a brute force analysis and see what happens. Okay. So, this is what one of the students had said, and let us try. So, the way you are going to do the brute force analysis is like this. So, this is my top PMOS, which happens to be diode connected, and this is my input. Let us call this input V1 with the understanding that V1 is nothing but VCM plus V in by 2 and V2 is nothing but VCM minus V in by 2. Okay. So, this is what we are going to do, and then over here I have got the current source, which I am not going to draw because this is a small signal diagram that I am drawing. Then over here I have got the second input device, which I am going to fold downwards and draw as a PMOS. Okay. And then finally on top there was a PMOS device, right, and I will fold that also downwards, and now I will draw it as an NMOS because it looks nice, with the caveat that the gate of this NMOS is actually connected up here. And suddenly the drawing looks very bad, right, and when these drawings look very bad, invariably the analysis is also going to be very bad. It is not going to be so straightforward anymore. We are no longer interested in two output voltages, we are interested only in one. We are only interested in this one and only this one output voltage. Okay. Unlike in our earlier brute force analysis where we had two output voltages, here we have only one. Okay. So, we are going to apply V1 over here, measure the output, we are going to apply V2 over here, measure the output. Overall it is going to be the combined response of V1 and V2. This is the plan. Okay. So, I have got V1. In the first instance, what we are going to do is we are going to connect V2 to ground. Okay. And to measure the voltage at the output, instead of measuring the voltage at the output, the way we have been doing is by using the Norton equivalent method, that is we look in from outside and measure the impedance, okay, number 1, and number 2 we apply a short over here and measure the current. Okay. So, these are the two things that we are going to do. Fine. Okay. Now, in step 1 you want to look in from outside and measure the impedance. So, this is the bummer, okay. This is a very difficult step over here. In this particular case, this long wire, this feedback wire is going to create a problem, okay, because looking down you are not so sure what is the impedance. Looking up you have some idea, but looking down it is different. Okay. So, let us be careful about it, but let us do it anyway. Okay. So, I am going to connect both V1 and V2 to ground, look in from outside and measure the impedance. So, I look in from outside, I apply a voltage over here, measure the current, that is the idea, right. Look in from outside, portion of the current will go up, portion of the current will go down. Now, just by the way, whatever current goes up gets pushed, right, it creates a voltage, that same voltage is applied on this. So, the same current is going to be pulled down. Okay, that is the current mirror action. Remember, we have just folded it up and it now looks, this looks like an NMOS, but this is actually the other half of the current mirror. Okay, so, looking up whatever current goes, looking down exactly the same current will go. So, effectively approximately the same current will go. So, effectively looking up whatever impedance you see, looking down you will see more or less the same impedance, which means that the net impedance is going to be half. Okay. I apply a voltage, some current goes up, equal current goes down, right. So, the net impedance is going to be half of the impedance that you see looking up. Fine, almost. Let us work it out. So, let us first look up and only up. When you look up, you are looking in from the drain of this PMOS, where the source is terminated by something. Okay, so, it is a formula. What is the source terminated with? So, you look in first over here and then you are looking in from the source of this NMOS, where the drain is terminated by something. And what is this something? This is a resistor of value 1 by Gm approximately, okay, or of value 1 by Gm plus Gmp. Okay. So, looking in over here, what do you see? Looking into the source, you are going to see whatever you had at the drain plus RDS divided by 1 plus intrinsic gain of the NMOS. By the way, this is actually a PMOS, this is actually an NMOS, this is also an NMOS, this is a PMOS in the actual circuit. Okay. So, right now I have drawn it differently, but these are actually, these are the NMOSs and PMOSs. So, the impedance looking up over here is what I have written. This impedance is this prime over here indicates that it is actually Gm plus Gmb. So, this is the impedance looking in from the source of the NMOS. Okay. Now, when I look in from the drain of this bottom device, then it is whatever was on the source times 1 plus the intrinsic gain. So, this entire factor cancels plus RDS n. Fine. I hope by now you have memorized the two formulae. Okay. Those two you see how we are applying the formulae, we are applying the formulae like, you know, it is bread and butter. Okay. So, this is the impedance looking up into the drain of this particular MOSFET. All right. So, I apply a voltage V, the current going up is V divided by so much. Now, this current eventually makes its way through this, the same current goes through this, all right, and it is going to create some potential over here. The same potential is going to be applied onto this MOSFET, all right, and therefore, this current, remember there is also RDS of this PMOS, this current is going to be the same current times this GM divided by GMP plus GDSP, all right. So, I apply a voltage V over here, the current going up, so V is the voltage I have applied, the current going up is V divided by this much. Okay. The voltage at the gate, let us call it something V mirror, is this current times that impedance. That is the voltage at the mirror. So, the current coming downwards is going to be that voltage times GMP. Fine. Is this okay? And there is now an additional factor. There is also an additional resistance of RDSP over here. Okay, that is also there. You have forgotten that. All right. So, therefore, what is the net impedance? The net impedance is the impedance looking up divided by not a factor of 2, but by a factor of 1 plus GMP by GDS, this factor. Okay, this is almost equal to 1. So, it is not going to be divided by 2, it is going to be divided by 1 plus almost 1, further in parallel with RDSP. So, my final output impedance this is the impedance looking up divided by a factor of 1 plus okay. This is the combination of the impedance looking up and the impedance looking down, further in parallel with RDSP. Is this analysis okay? This is the impedance looking in, and this suffices, this experiment is going to suffice for both application of V1 as well as application of V2. For both you get the same answer. Okay. So, two experiments in one shot, the output impedance. Then we are going to apply V1, measure the short circuit current, apply V2, measure the short circuit current, and then finally we will apply we will see the net response when I apply both V1 and V2 at the same time. This is the plan. This is the first experiment in the 3-part experiment, first part. Okay, this is okay. You want to simplify this? I like simplifying, right. I do not like such huge complicated expressions, right. So, you can multiply numerator and denominator by 1 plus GMP RDSP, that looks the obvious thing to do, and when you do that, this is what you end up with. Further, in parallel with RDSP. Okay. So, this is little more tractable, and then how will you deal with this? You want to place it in parallel? Okay. And then generally what is done is you are going to multiply by these two factors, numerator as well as denominator. So, then and then add. Okay. This is just algebra. Okay. And then you can combine the two. So, you get 2 times RDSP in the denominator, 2 RDSN, 2 times this. So, the 2 factor actually can come out. And 2 times GMP RDSP squared. Okay. And in the numerator, what do you have? You have got RDSP, 2 RDSN plus 2 GMP RDSP RDSN. Okay. The whole thing times RDSP. Fine. This is pretty much the impedance. Notice there is a factor of half, right, that tells you that the impedance is half of the output of the impedance looking up. So, that is why that factor of half showed up really, all right. So, the impedance, these are small numbers compared to GMP, RDSP, RDSN and GMP, RDSP, RDSP. So, the net denominator is nothing but GMP, RDSP times RDSN plus RDSP times 2, that is the denominator. And in the numerator what do you have? These two are again small, so you do not worry about it. You have got GMP, RDSP times 2 RDSN times RDSP, all right, and then you have to look at what remains. Okay, so a lot of things are going to cancel out. All right, so this is the output impedance story. So let us keep this on the stack, and now we are going to do the remaining 2 experiments. And the remaining 2 experiments, you see, this is much harder, right? This business, this brute force business is much harder than our hand analysis, our earlier analysis, where we just did a little bit of approximation. So, being accurate always comes at a cost, right. In this case the penalty is a lot more, right. You really have to work hard on the problem to be precise. Okay. So, a lot of times this precision is so costly that you do not bother about it, and you just do engineering. So, if you want to do engineering, that is the way. If you want to do maths and you want to be absolutely accurate, then this is what we are doing right now. We should not be doing this, and this is something that I am doing because someone said over here that why do not we do it the brute force method. This is also a pointer to see how hard the problem becomes. Okay. So, now short circuit current. So, this gate is actually hooked back over here, all right. Now, what we have done is we have applied V, and V is going to create some current over here. We do not, let us not worry about what that value is. It is going to create some current. That current is certainly going to go through the short circuit, but this current is going to create a voltage. The same voltage is applied here. So, an identical mirror copy of the current is going to be created here. So, the current here is coming downwards, right. The mirror will also do a downwards, but when you turn it, it is going to be an upwards current. Fine. So, you have 2 components to the current. One is coming because of the PMOS, the other is coming because of the mirror. All right. So, the net short circuit current is going to be double approximately. Okay. And by now you have figured out the mirror ratio, that is, if this current is some I, then this current is going to be I times 1 plus, sorry, I times GMP by GMP plus GDSP, right. Is there going to be current in RDS? No, because it is a shorter, okay, no current in RDS. So, at least that part is gone, and that is it. Okay. So, the net current is going to be I times 1 plus GMP divided by GMP plus GDSP. Okay. Now, all I have to work out is what is this I current. Okay. And this is nothing but the bottom side of the common drain circuit. The drain is at ground, right. This is the bottom side. Think of this as an NMOS. You apply a voltage at the gate of the NMOS, the drain is at ground, the source is terminated with some impedance. What is that impedance, by the way? What is the impedance? Looking up over here, you are looking into the source of the MOSFET, the drain is terminated with something. That impedance is nothing but, yeah, we had computed it earlier, right. So, the drain is terminated with 1 by GMP plus GDSP, that is what the drain is terminated by. But looking in from the source, what you have is this divided by, so this plus RDS N, at the end of the day this is NMOS, this is also NMOS. So, be careful, this is PMOS. So, whatever is on the, so I am looking in from the source to find the impedance. What is on the drain divided by, what is on the drain plus RDS N divided by 1 plus the intrinsic gain. Okay, that is this impedance. So, my problem looks like this. This is I current. What is the value of I? If I apply V over here and I terminate the source is terminated with this impedance. Let us call this impedance, Z prime. This is the common drain circuit, and we know how to solve this because we know the voltage over here. What is the voltage over there? The voltage has an approximate gain of 1. Okay. So, if this is V, the voltage over here is V times GM by GM plus non-idealities. Biggest non-ideality over here is GMB, which makes this GM prime, GM plus GMB, I am writing it as GM prime, plus the other non-ideality is GDS and the other non-ideality is Z prime. Okay. That is the voltage over there. Now, if that is the voltage over there, then the current I is this voltage times G prime. And generally a good idea is to multiply numerator and denominator by Z prime when you have got both. Okay. So, this is what we have. The other thing is sometimes you have got GDS, this is GDS of N. Okay. Here you have got RDS of N. So, one thing that you can do is just, alright, you want to change this or this, it does not matter. Okay, multiply numerator and denominator by GDS N over here. Okay. Now, Z prime has a denominator and that is being multiplied by the same denominator. So, Z prime times this factor is nothing but whatever is in the numerator over here. And then you have got 1. Okay. So, this is my I, but my final short circuit current is I times 1 plus so much. Okay. So, let us write it out. So, my I short circuit when I have applied V1 or V2, which one did I apply? I have applied V2. So, I have applied V2 and I got a current I in this case. First I applied V2 and I got a current I. Okay, this was the current that I got when I applied V2. Now, this current times 1 plus GMP by GMP plus GDSP is the total short circuit current. And obviously, what you are going to do is multiply numerator and denominator by GMP plus GDSP. Fine. So, I applied V2, I got a short circuit current. In the next step, what we are going to do is, we are going to apply V1 and find out a similar short circuit current. And then we are going to combine the two short circuit currents. I already have the output impedance. Put all of these together, finally you will come at an expression which gives you the gain. Lot of hard work. Do you want to continue doing that? You want to continue, because it's really a lot of hard work that we are doing, and finally you will come up with an expression. We can do it. Okay, this brute force method will work. Okay, we will apply V1, drain is terminated with a resistance. Okay. On the source side you have some complicated resistance. So, this is going to look like a source degenerated amplifier. Look, this is how the analysis goes. The analysis is always going to boil down to a one transistor circuit, right. Then you recall what you did for that one transistor circuit and play it out on paper. Okay. That is how it is going to work out. So, I am not going to bother with this. Your answer is finally going to come down to the same thing, to something close by, right. It is not going to be exactly equal to our initial result. It is not going to be exactly equal to this, but it is going to be close. All right, is this okay? So, this is the idea of the self biased active load differential amplifier. This is what we did, right. We wanted to do a brute force method. So, in the brute force method we applied V1, found out the short circuit current over here, applied V2, found out the short circuit current over here. We did not really, we actually only did V2, we did not really do V1, right. V1 was harder, because V1 if I apply, then on the source side I have got something more complicated. There is all of this on the source side, right. On the drain side I have got this, and then I have got the current mirror. Okay. So, every time I have got the current mirror, you know, an extra current is going to get pushed in to the short circuit. Fine. Eventually, you will do all of this analysis, you will come up with exactly the same answer, and therefore, what I am trying to say is, let us not worry about it. You do these analyses in your free time. I am telling you how to do it, but I do not want to do it in active class time, class minutes. All right. Maybe one possibility would be that as a handout, I could solve this entire thing and give it to you as reference material, so that you see how the whole analysis has been done. Okay. So, next we have learnt a few things. First thing that we have learnt is our basic differential amplifier, resistor, differential amplifier. Then we said, let us get rid of the resistor, place an active load over there. Okay. We did the analysis of input common mode range. We figured out what are the swing issues over here, what is the largest voltage, smallest voltage, what is the voltage range at the input, and correspondingly what is the voltage range at the output. We figured all of this thing out. Then we also studied the self biased active load differential amplifier, where we do not need an extra current mirror. The current mirror is built into the circuit, but of course, this circuit breaks the symmetry, and when symmetry is broken, the analysis becomes very hard, but in this particular case the answer can still be worked out with some sort of a intuitive symmetry. Okay, your answer, what is the final gain of the circuit? Sorry, what is the final gain of this circuit? If this is V in by 2 input signal, this I is GM times V in by 2, the same I, GM V in by 2, GM V in by 2, what goes out is, what goes out? GM V in, current goes out, and this GM V in current develops across the load. So, your answer is in terms of voltage, this is your voltage at the output. Okay. So, your gain is still GM times RDS N in parallel with RDS P. Your gain in terms of output voltage divided by input differential voltage, output voltage divided by V1 minus V2 is going to be GM times RDS N in parallel with RDS P. Fine. What would have happened if this was symmetric? If this was symmetric, you would have broken it up into half circuits, right. In each half circuit, you are applying V in by 2, this is now ground, you have applied V in by 2. Okay. So, the short circuit current is GM V in by 2. Output impedance is RDS of N in parallel with RDS of P, this is not there. Okay. So, output impedance is RDS N in parallel with RDS P. short circuit current is GMV in by 2. Okay. So, the voltage at the output is going to be minus GMV in by 2 times RDS N parallel with RDS P. The differential voltage, in one you have applied V in by 2, in the other you have applied minus V in by 2. So, the differential voltage will be double, and therefore, you will get exactly the same differential voltage in the other case. In the symmetric case, you will get exactly the same differential voltage. So, in that case also V out, it is no longer just one node voltage, it is the difference between two voltages. That will also be exactly the same, it will be GMV in RDS N in parallel with RDS P. Okay. And therefore, the gain between the differential output and the differential input is going to be exactly the same. Okay. In this case, it is single ended voltage by differential input. In that case, it is going to be differential output by differential input. The gains happen to be equal. Okay. How strange is that? So, effectively it is almost as if this will have double the gain, almost as if. Okay. It is not quite right, this does not have double the gain, this has the same gain, just that one node is swinging double what the other two nodes were swinging each. Okay. This one node has a voltage which is double of the individual nodes in the other case, but the difference between the individual nodes in the other case is the same as this voltage in this case. Okay. What about this node? What about this node? Is this node moving? This node is not moving around at all. Okay. I am producing I current, this I current is coming through a diode. The diode has a low impedance, the impedance is 1 by GMP. Okay. So, the voltage that it produces is almost nothing, it is V in by 2 times GM, that is the current, divided by GMP plus GDSP. Okay. So, if I apply V in by 2 signal over here, this node is swinging, I mean changing by GM by GMP times V in by 2, which is almost as if saying it is not swinging at all. Its amplitude is similar to the input amplitude. If the input amplitude is small, this amplitude is also very small. Okay. So, the gain between here and here is nothing, almost nothing. Okay. So, what happens over here? In this circuit, this node is more or less static, this node goes double, whereas in the symmetric case, this node comes down, this node goes up by equal amounts. All right. Is this, are you getting the clarity over here? What is happening? What is the difference between this self-biased load and the ordinary ordinary load? You are understanding the difference? In this case, the voltage here is more or less constant. This is oscillating, or this has a gain of 2 times. In the other case, this has a gain of minus, this has a gain of plus 1. Net difference is 2. All right. So, this is your self biased active load op amp, active load amplifier. Now, what is it going to take? You see, I just mentioned op amp. What is it going to take for us to make an op amp? We now know how to make a differential amplifier. Okay. A differential amplifier is amplifying the difference between the two inputs, and it is almost as if we have managed to make this triangle, right. The objective of the course is to make this. One important objective of the course is to know how to make this particular building block, what is inside this triangle. Okay. Now, is that it? Could this be what is inside this triangle, or do you need more? You need more. Why? Because you need more gain. This will provide you a gain of Gm times RDSN in parallel with RDSP, right, which is less than the intrinsic gain of the MOSFET. If the intrinsic gain of the MOSFET is 100, then maybe this amplifier over here will give you a gain of 50. We do not want 50, we want 1000, we do not even want 100, we want 1000, we want 5000, we want a large gain. Okay. 1000, a gain of 1000 is probably a bad op amp, right. Gain of 10,000 will give is a reasonably good op amp, right. Gain of 1000 is the lower limit of what the gain of an op amp should be. Okay. So, we need to increase the gain of this circuit. How are we going to increase the gain of this circuit? There are two ways, one is cascade, the other is cascode, right. We studied long back, one cascade, the other cascode. Okay. So, the cascade is rather straightforward, you just put two diff amps one after the other, all right. The cascode, let us look at the cascode, because the cascade is so easy. Let us look at the cascode. You see, in case of the cascode, the small signal circuit, the small signal half circuit needs to look like a cascode amplifier. And my cascode amplifier look like this. Normally this is drawn flipped. Okay, I flipped it around because there is no space, but this is the normal structure of the cascode amplifier. Now, what is the benefit? The benefit is that the output impedance is very large. Output impedance over here is the output impedance looking down, which is intrinsic gain of this MOSFET times RDS of the lower one plus RDS of the top one, in parallel with intrinsic gain of this MOSFET times RDS of the topmost one plus RDS of the lower one. So, this is a large output impedance. At the same time, the short circuit current is approximately Gm of the bottom transistor. Why? Because I apply a voltage V, it produces a current Gm times V. This current has to choose between going through RDS and looking into the source of the second MOSFET. And looking into the source of the second MOSFET, it sees a low impedance because all of this is shorted, right. It sees a low impedance looking into the source of the second MOSFET. How low is it? It is 1 by Gm of this MOSFET as opposed to going through RDS of this. So, approximately Gm is the transconductance. Okay, Gm of this bottom MOSFET is approximately the transconductance. Output impedance is Gm of top device times RDS of top device times RDS of bottom device in parallel with Gm of this one, RDS of this one, RDS of this one. That is the output impedance. So, net gain is Gm of NMOS times the output impedance, which is the second Gm the intrinsic gain of the second device times RDSN in parallel with intrinsic gain of this device in parallel with times RDSP. Fine. So, this was the cascode amplifier, and is there a way that I can make this cascode amplifier as a differential amplifier? And the answer is yes, very easily. All I have to do is make sure that this is the differential mode half circuit, which means that I just make another branch over here, which is a mirror image, and place a current source at the bottom. And now I will apply a differential input signal, common mode input signal. The differential input will be amplified, the common mode input will be suppressed, right, and all of this is going to happen exactly the same way as before. Now, we are going to study this further. There are certain limitations of this. This is a very good circuit, but there are a lot of limitations. So, we will study this further in the next class. Thank you.